Uh, Hi everyone. I hope you are doing good. Today's we are going to cover the topic electrostatic potential and capacitance. Example 2.4 to 2.5, NCERT Section 2.7 to 2.8. Now we are going to see what topics we are going to cover today. Disclaimer. The images, text, and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the content immediately. Please note that the parts of the content may have been generated using generative AI, which is experimental. So, the topics we are going to cover today. First one is 2.7 potential energy of a system of charges. Example 2.4 potential energy in an external field, potential energy of a single charge, potential energy of a system of two charges in an external field. Example 2.5 and potential energy of a dipole in an external field. So let's begin. So our first topic is to derive the expression of potential energy in two charge electrostatic systems. Let's consider to calculate the work done in building configuration of two charges. So before doing this topic, you must have the knowledge of potential energy and potential due to a point charge. So now we are going to calculate the potential energy of system of charges when there is more than one charge. So let's consider to calculate the work done in building and configuration of two charges Q1 and Q2 with position vectors R1 and R2 relative to an origin. Now there are two charges. First one is placed at a position vector R1 and second charge is placed from the origin with position vector R2 like this. So here position vectors are not shown, but this is Q1 charge, this is Q2 charge. The position of this Q1 with respect to origin is R1. The position of this Q2 charge with respect to origin is R2. And the distance between them is R12. So initially both charges are at infinity. And potential energy of the system is 0 when they both are at infinity because there is no interaction between them. Now, and we determine the work done by an external agency to bring them to their final positions. Now, what is the work done or potential energy of the system? When we bring them close and form a configuration, then there must be a work done. Work done to put these charges near each other. And this work done is equal to the potential energy of the system. Now to this figure again, when charges Q1 is brought from infinity to point R1. Let's suppose this is point R1 because Q1 has position vector R1 with respect to origin. Okay, this is understandable. Okay, so when charge Q1 is brought from infinity, we are bringing charge Q1 from infinity to that point at a distance R1 from the origin. So when there is only one charge, there is no external field, there is no electric field due to any other charge. So from bringing this Q1 from infinity to any point where there is no electric field or electric potential, no work is done as there is no external field initially. To bring Q1 charge only, Q2 still is at infinity. We are only bringing Q1 charge first. So bringing Q1 charge to that point from infinity requires no work. Now, what we gonna do now? The charge creates now. This Q1 charge is at this point. Now it will create potential in the space. Potential due to point charge. What is the potential due to this Q1 charge? 1 by 4 pi epsilon naught Q1 by R1P. Where R1P is the distance of point P from Q1. Any point P1 in the space. any point, arbitrary point, any point P, here, or here, anywhere. So the potential due to this Q1 charge at any point or at any arbitrary point P is this, where R1P is the distance of point P from Q1. So this is the potential created by this Q1 charge around the space. Now we are going to bring Q2 charge from infinity to that point. Now we will see how much work should be done. Again this picture diagram. Now the work done in bringing Q2 charge from infinity to R2 equals Q2 times the potential at R2. Now we are bringing this charge from infinity to that point. Now there is external field or potential due to this Q1 charge exists in the space. Now we will have to do some work to overcome the force of repulsion, and that work is equal to Q2 into potential created by this charge. So work done in bringing Q2 from infinity to R2 equals to Q2 times the potential due to Q1. Okay, so what it will become? This Q2 into potential created by Q1 charge. What is the potential created by Q1 charge? 1 by 4 pi epsilon naught Q1 upon R12. This is the potential created by this Q1 charge at this point. Okay, so we are simply multiplying the potential created by this Q1 charge at this point into Q2. So this is the work done in bringing Q2 charge from infinity to that point, where R12 is the distance between the points R1 and R2. So R12 is the distance between these two charges. So this is the work done in bringing the Q2 charge at that point, and hence this is the total work done to form a configuration of two charges, these two charges. Okay, so this is the total work done. Since electrostatic force is conservative, so the work is stored as the potential energy. So that work we have done to build this configuration is stored in the form of potential energy, which is equal to U equal to 1 by 4 pi epsilon naught Q1 Q2 upon R1 2. So this is the potential energy of two charge system. The expression remains valid regardless of how the charges are brought to their position due to path independence of work for electrostatic force. We are not concerned that how these charges are brought to these points. From here, from this path, from this path, from this path, we are not concerned about the path. We are only concerned about the initial and final position. Initial position of these both charges is infinity, and final position of these both charges is this point and this point, and distance between them is this. We are not concerned about the path or the way we bring these charges to these points. So the expression remains valid regardless of how the charges are brought to their positions due to path independence of work for electrostatic forces. Now, to derive the expression of potential energy in three-charge electrostatic system, we have seen the two-charge system. Now, what we will see? Three-charge system. Concept is same, but the additional charge is being introduced. Now, for like charges, if the charges are of same polarity, positive positive or negative negative, product of these both charges will be greater than 0. If both are negative, still the product of these both will be greater than 0. If both are positive, then also the product of both charges is greater than 0. So potential energy is positive. If we want to bring a positive charge near positive charge, then potential energy stored is positive. If we bringing minus q charge near minus q charge, then also potential energy is positive. But if the polarity is inverse, one charge is positive, one charge is negative, then the potential energy stored will be negative. For unlike charges, Q1, Q2 product of both charges will be less than 0. Hence potential energy stored is negative. Now this is the 3 charge system, Q1, Q2, Q3. We have to make this configuration. Firstly, what we will do, steps are same, concept is same. First we will bring this Q1 charge here, then we will bring Q2 charge here, then we will bring Q3 charge here. So what are the steps? First we will bring this Q1, then no work is done because no other charges are present at that time. Now after bringing Q1, we want to bring Q2 at that point. Now what will happen? We have to do some work because Q1 is present already. So due to the potential or due to the electric field created by this Q1, we have to do the work to overcome the force of repulsion to bring the charge Q2 here. Now this configuration is formed Q1, Q2. Now we have to bring this Q3 charge here. Now what will happen? Q3 have to overcome the electrostatic force of these both charges. So Q3 charge, we have to bring this Q3 charge here. So at this point, potential due to Q1 and Q2 will be considered. Okay. Now we will see how. Potential energy of a system of 3 charges is given by equation 2.26 with the notation given in the figure. For a system of 3 charges Q1, Q2, Q3 at position R1, R2. These positions R1, R2, R3 are with respect to the origin. So this Q1 is at R1 distance from origin. Q2 is at R2 distance from origin. And Q3 is at distance R3 from origin. Okay. So first bringing Q1 requires no work. As I have already mentioned and we have already seen in 2 charge system that when all these 3 charges are at infinity, we have to bring this Q1 charge at this point. So there is no other electrostatic field or potential present. So this Q1 requires no work. So now secondly, we have to bring Q2 charge. So the work to bring Q2 is 1 by 4 pi epsilon naught Q1 Q2 R12. Okay, this is up to 2 charge system which we have done already. Up to 2 charge system, what is the total work done? This. Now we have to bring third charge also in the configuration. Now the charge Q1 and Q2 creates potential. Now the potential created due to these both charges will be 1 by 4 pi epsilon naught Q1 by R1P plus 1 by 4 pi epsilon naught Q2 by R2P, and taking common 1 by 4 pi epsilon naught, which we will get 1 by 4 pi epsilon naught Q1 by R1P plus Q2 by R2P. P is any arbitrary point where we have to find the potential due to these both charges. Okay, so potential created by these both charges is this. Now work done to bring Q3 charge at a distance R3 from the origin. Now V1 to R3 is equal to 1 by 4 pi epsilon naught Q1 Q3 upon R13 plus Q2 Q3 by R23. What we have done here? We have multiplied this Q3 charge with the potential created by other 2 charges. So potential created by other 2 charges 1 and 2 is this. Now work done to bring Q3 charges, charge multiplied by the potential created by other charges. So Q3 is multiplied by this potential. So Q3 is multiplied by this. So what we get 1 by 4 pi epsilon naught Q1 Q3 R13 plus Q2 Q3 by R23. This is the work done to bring Q3 charge into the configuration. This is the work done to bring Q2 charge. this is the work done to bring Q3 charge. And work done to bring Q1 charge was 0. Now we will calculate the total work done. What is the total work done? Hence, total potential energy is 1 by 4 pi epsilon naught Q1 Q2 R12 plus this work. And after taking common 1 by 4 pi epsilon naught from all the total work, then it will become 1 by 4 pi epsilon naught Q1 Q2 by R12 Q1 Q3 by R13 plus Q2 Q3 by R23, which is independent of the assembly sequence due to the conservative nature of forces. Again, what is this? What this mean? Which is independent of the assembly sequence. This means that we are not concerned with the path or sequence, that first Q1, it is not necessary that Q1 charge is brought first, or it is also not necessary that Q3 charge is brought first. We can bring any charge at any sequence. We can bring charge Q2 first, then Q3, then Q1, any sequence. And also it is sequence independent, also it is path independent. We are only concerned with the final configuration. Now, there is an example. 4 charges are arranged at the corners of square ABCD of side D as shown in the figure. Find the work required to put together this arrangement. And B part is a charge Q0 is brought at the center E of the square. The 4 charges being held at fixed at its corner. How much extra work is needed to do this? So this is the diagram. We have discussed about the 2 charge system, 3 charge system. This is 4 charge system. So now the configuration is this. We have to arrange the charges in this configuration in the form of square. Okay, so concept is same. First we will bring first charge, then we will bring another charge, then we will bring third charge, and one additional step in this, instead compared to previous topic, we have to bring another fourth charge into the configuration, and then we have to calculate the total work. Okay, so find the work required to put together this arrangement. First part is this, and second part is we have made this configuration. Now we have to bring this Q0 charge at this E point at the center of the square. So how much extra work is needed to do this? We have to do this 2 parts. Okay. Okay, first part, what we are going to do, since the work depends on the final arrangement. Okay, we are concerned with final configuration, not the path, not the sequence. And note on how they are put together. We calculate the work needed for one way of putting the charges at A, B, C, D. Okay. Firstly, we will bring the charge at A, then B, then C, then D. And distance between side of the square is D. Suppose first the charge plus Q is brought at K. Firstly, we will bringing the charge plus Q at A. Okay, at this point. And then the charges minus Q, and then plus Q, and then minus Q to B, C and D. We will follow this sequence. We can follow any sequence, but we will follow this sequence A, B, C, D respectively. Now the total work needed, that can be calculated in steps. Firstly, we will calculate the work done to bring this charge, then to this charge, then this charge, then this charge. First, work needed to bring charge plus Q to A when no charge is present elsewhere is 0. Because these 3 charges are not present initially. They all are at infinity. Then to bring this plus Q charge at A point is 0 because no other charge is present. So there is no another external electrostatic field. So work done to bring this charge is 0. Second, work needed to bring minus Q to B when plus Q is at A. Now we have brought plus Q at A. Now we are going to bring this minus Q at B. So this minus Q will be affected by this plus Q charge at A. Okay, so what is the work done? Work done is this charge into the potential created by this charge. Minus Q charge at B into the potential created by this positive plus Q charge at A at B point. This is given by charge at B into electrostatic potential at B due to charge plus Q at A. So potential produced by this plus Q at A at B point. Okay. Equal to minus Q. The charge at B is minus Q into potential created by this plus Q charge at B is Q square Q by 4 pi epsilon naught D. What is the distance between these two charges? D. Equal to minus Q square 4 pi epsilon naught D. This is the work done to bring plus Q minus Q charge at B. Okay. This is the one work. Now, again this diagram. This charge is present here. Potential of this charge on this point into the charge minus Q is the work done to bring this minus Q charge at this point. Okay. Now, work needed to bring charge plus Q to C. Now, there is charge minus Q present at B. There is a charge plus Q present at A. Now, we are bringing plus Q at C. And what is the work done to bring charge plus Q at C when plus Q at A and minus Q at B is present? Okay, these two charges are now present. This charge, and this charge is present. This charge and this charge. Okay, so work needed to bring plus Q charge. Now we are going to bring this plus Q charge at C. Okay, this is given by, now what is the work done now? Charge at C, this plus Q into potential created by these two charges at C. What is the potential created by these two charges at point C into the charge at C? This is the total this is the work done to bring charge plus Q at C when these both charges are present. Now, charge at C is plus Q. What is the potential at C due to A and B? This is the potential at C due to A. A is here. What is the potential created by A at C? Q by 4 pi epsilon naught and this distance. This distance. What is this distance according to Pythagoras theorem? This D, D square, 2D square root 2D. Okay, this is the potential created by this A at C, and this is the potential created by this minus Q at B on this C, minus Q 4 pi epsilon naught, and this distance is T. So charge at C into potential at C due to charges at A and B. So this is the work done to bring this positive charge at C when both these charges are present. Okay, so after solving or rearranging, we got this. Work done to bring C positive charge at C. Now, work needed to bring minus Q at D when plus Q at A, minus Q at B and plus Q at C is present. Now, three charges are present. One is positive Q at A, negative Q at B and positive Q at C. Now, we have to bring the fourth charge at D. So, what is the work done now? And this is again same concept, charge at D into potential at D due to other three charges A, B and C. Okay, what is the charge at D and potential at D due to charges at A, B and C? Now these three charges are present, A, B, and C. Okay, now what is the work done to bring this D minus Q at D? Charge at D point into potential created by these three charges at this point. Okay, so minus Q, this is charge at D. This is charge at D. Now plus Q by 4 pi epsilon naught D. This is the potential created by this positive charge on this point. Q plus Q by 4 pi epsilon naught. What is the distance between these two charges? D. Plus minus Q by 4 pi epsilon naught root 2 D. This is the potential created by this minus Q charge at B on this D point. And the distance between these two charges is, again, this is D, this is D. D square, 2D square root 2D. Okay. Plus Q by 4 pi epsilon naught D is this. Potential created by this positive charge at C at this point. This is the potential created by 3-point charges A, B, and C on this D point into the charge at D. This is the work done to bring this minus Q charge at D due to all these three charges present. So after solving and rearranging, we got this. Minus Q square 4 pi epsilon naught D 2 minus 1 by root 2. So now we have calculated the work. Work done to bring this plus Q charge is 0. This minus Q charge is something we calculated. Plus Q charge at C is also we calculated. And plus minus Q charge at this D point also we calculated this. Now total work done is the sum of all these work done. Add the work done in steps 1, 2, and 3, and 4. The total work required is this. At first charge, work done is 0. Another, we are taking this term common. So after second work done to bring second charge is this into 1, means this term. Work done to bring the third charge is this term into this. And work done to bring 4 charges, this into this. We are taking this common. And after solving, total work done comes out to be this. Q minus Q square upon 4 pi epsilon naught D 4 minus root 2. This is the total work done to make the configuration of 4 charges. The work done depends only on the arrangement of charges and not how they are assembled. So we are not concerned with the sequence and path. By definition, this is the total electrostatic energy of the charges. Okay, B part. What was the B part? The extra work necessary to bring a charge Q naught to the point E when the 4 charges are at A, B, C, and D. Now, the configuration of this square, you have seen 2 charges are negative and 2 charges are positive, and all these charges are at equal distance from the center. So positive potential to 2 positive charge cancel out the negative potential due to other 2 charges, because 2 charges are positive, 2 charges are negative, and the distance of all the 4 charges from the center is same. Okay, so what is the extra work necessary to bring a charge Q naught to the point E when the 4 charges are at A, B, C, and D? Q naught, that is the charge we have to bring into electrostatic potential at E due to all the charges A, B, C, and D. This. All these charges are at equal distance from this E point, because this E point is at center. And potential due to these 2 negative charges cancel out the potential due to these positive charges. The electrostatic potential at E is clearly 0, since potential due to A and C is cancelled by due to B and D. Hence, no work is required to bring any charge to point E. So there is no work done, 0 work done to required to bring any charge to this point E. I hope you understood. Okay, next topic, potential energy in an external field. Now, Firstly, we will deal with the potential energy created by another charge. There are two charge system, and to bring a second charge into the configuration, we were considering the potential created by first charge. Now we are going to see the potential energy in an external field. Okay, that work at E is 0 because the potential at center due to 4 charges, 2 are negative, 2 are positive. So potential due to positive charges and potential due to negative charges at the center is 0. Since potential is 0 at the center, so what is the work? Work is equal to Q into potential difference. So potential is 0. So work is also 0 to bring any charge to this point E, because the potential at center of the square due to other 4 charges is 0. Now here we focus on some assumptions to find the potential energy of charges in an external field. Field E is produced by external sources, not by given charges. Now the field we are considering is produced by external sources, not by the given charges. Firstly, we will consider the field produced by the charges which are in configuration. Now we will also consider the external field. External field E or potential V may be specified without knowing their sources. We are not concerned with the sources that are producing this external field. We also going to know about the value of this field or potential. We are not concerned about which sources are producing this external field. We assume the charge Q doesn't significantly affect these external sources, which hold true when Q is very small or when external sources are fixed. So we are assuming that the other charges we are considering in external field doesn't significantly affect the external sources. Okay, so we will consider that external field is stronger. So these Q charges, field produced by these charges will not affect the external field, which holds true when Q is very small or when external sources are fixed. Even with finite Q, its influence can be ignored. Even if we take Q as significant, not very small, also then influence can be ignored when strong sources at infinity produce a finite field E in the region of interest. So even Q is not small, we will consider that the external field produced by any source is very strong in this region. So potential energy of a single charge. Now we will discuss what is the potential energy of a single charge in external field. By definition, V at P represent work done in bringing a unit positive charge from infinity to P with potential at infinity taken as 0. Okay, what is the definition of potential? Work done in bringing a unit positive charge from infinity to any point P with potential at infinity to be taken as 0. Therefore, work done in bringing charge Q from infinity to point P in the external field is Q into V. This is we have already done. This work becomes the potential energy of Q. So that work we are doing in bringing a charge Q from infinity to point P is stored in the form of potential energy. Now for a position vector R, the potential energy is given by, okay, this VR. Now this potential is created by the external field. Okay, so we don't know the source. So we cannot apply the formula. We don't know the source. Where the source is? We only know that there is an external field. So this potential is due to the external field, and this is the Q charge which we are going to place in the external field. So potential energy of Q at R in the external field is Q into VR. For example, an electron whose charge is Q is equal to E, which is 1.6 into 10 to the power minus 19 coulomb, accelerated by potential difference 1 volt, gains energy of Q into potential difference, delta V equal to 1.6 into 10 to the power minus 19 joule. What is this term called? 1 electron volt. 1.6 into 10 to the power minus 19 joule is 1 electron volt. This unit is widely used in the atom, nuclei, and other quantum physics topics. So this unit is commonly used in atomic, nuclear, and particle physics. That are the topics of 12th class at the last, modern physics. This electron volt will be we are going to use very much in the last chapters of 12th class. So this unit is commonly used in atomic, nuclear, and particle physics with various multiple as 1 kilo electron volt is equal to 10 to the power 3 electron volt, which is 1.6 into 10 to the power minus 16 joule. 1 mega electron volt is equal to 10 to the power 6 electron volt, equal to 1.6 into 10 to the power minus 13 joule. 1 giga electron volt is 10 to the power 9 electron volt, which is equal to 1.6 into 10 to the power minus 10 joule. And 1 tera electron volt is 10 to the power 12 electron volt, which is equal to 1.6 into 10 to the power minus 7 joule. Now, potential energy for a system of two charges Q1 and Q2 at position R1 and R2 in an external field involves multiple steps. Initially, when bringing Q1 from infinity to R1. Now, R1 is the distance from origin we are taking generally. Okay. So, when we are bringing Q1 charge from infinity to any point R1, any means any point which is at distance R1 from the origin, the work done is Q1 and potential at that point due to external field. This is the potential at R1 distance from origin, means any point which is at R1 distance from the origin. So this is the work done. Q1 charge we are bringing into the potential due to the external field. For the second charge, work is done against both. Now we are going to bring another charge. When we have done the last 2-3 topics before this, in which we are not considering the external field. So work done to bring Q1 charge there was 0 because there was no any another field present at that time. But here work done to bring this first charge is also something non-zero, Q1 into, because external field is existing, due to which potential is non-zero at that point. And to bring the second charge Q2, what was we considering at the, in previous topic, we was only considering the potential due to this Q1 charge. Now to bring the second charge, we have to consider now both the external fields. One is produced by this Q1 charge, one is external field. We have to consider the work done against both the external field. One is due to this Q1 and other is external field. Work done against the external field equals to, now work done against the external field here is Q1 V R1, and work done against the external field by Q2 charge is Q2 into VR2. Okay, while the work done against Q1's field, now Q1 is also present there, so there must be electric field due to Q1 also. So Q2 has to overcome the both the fields. First is external field and second is field produced by this Q1. So now the work done against this Q1's field is Q1 Q2 by 4 pi epsilon naught R12, where R12 represents the distance between the two charges. Using the superposition principle, the total work done in bringing Q2 to R2 is this. Q2 VR2, this is the work done against the external field, and this is the work done against the field of Q1. Therefore, the system's potential energy and hence the total work done. What is the total work done to make the two charge configuration is? The work done to bring the charge Q2 is this, and work done to bring the charge Q1 was Q1 VR1. So total work done is Q1 VR1 plus Q2 VR2 plus this. This is the work done against the external field by Q1. This is the work done by against external field by Q2. This is the work done against external, sorry, this is the work done against the field produced by Q1. Now, example, determine the electrostatic potential energy of a system consisting of two charges. There are two charge system, okay, with no external field. There is no external field present there, placed at minus 9 centimeter 0 0, which is at negative x-axis, minus 9 centimeter, and one another charge is present at 9 centimeter positive x-axis, and other two axes are have value 0 respectively. Second part is how much work is required to separate the two charges infinitely away from each other. Now we are forming a configuration and we are bringing charges from infinity. Now again, after forming the configuration, we are separating this charge and separating these two charges infinitely away. Now what is the work done? The work done is equal in magnitude but opposite in direction in both these cases. The work we have done to bring them into configuration is the work to separate them. They are equal in magnitude, but the direction is, the sign is different. We will see it in the solution. Third part is, suppose that the same system of charges is now placed in an external field. Now we have to do this thing with the external field. The external field is equal to A 1 by R square. Okay, and this external field is not constant. This is varying with R square. And the value of this A is 9 to 10 power 5 Newton per Coulomb meter square. What would be the electrostatic energy of the configuration now? Okay, these are the three parts. Okay, what was the first part? Two charges 7 microcoulomb and minus 2 microcoulomb were present. One is at minus 9 centimeter, one is at 9 centimeter on x-axis. So the distance between them is 18 centimeter. Okay, so what is the potential energy of this system? 1 by 4 pi epsilon naught Q1 Q2 by R. R is the distance between them, that is 18 centimeter, and in meters it is 0.18. And this is the value of 1 by 4 pi epsilon naught. This is first charge Q1, which was 7 microcoulomb, and another is minus 2 microcoulomb, and this is the micro is 10 to the power minus 6. So both the micro 10 to the power minus 12, and which will result in minus 0.7 joule. Okay, so this is the potential energy of the system. Why it comes out to be negative? Because both the charges are of different sign. We have discussed, if the two charges have different sign, then product of these charges will be less than 0, hence potential will be negative, potential energy will be negative. Now second part, how much work is required to separate the two charges infinitely away from each other? This is the same work that is stored in the form of potential energy, but the sign is opposite. Now what we are doing, we are separating these charges and putting them at infinity. So U2 minus U1, final minus initial. Final potential energy, we are separating them up to infinity. So final potential energy will become 0. Initial potential energy was minus 0.7. So put the minus 0.7 here. So this will result in 0.7. So the same work done, but the opposite sign. Now we are separating them. Okay, third part was, now charges are same and coordinates also same. What is changed now? There is external field also, which was like E was equal to A by R square, which was varying with distance square, and A was 9 into 10 power 5 Newton meter square per coulomb. Now, what was the potential energy now? This is the Q1 VR1. This is the work done to bring Q1 charge in an external field. This is the work done to bring Q2 charge in an external field. Okay, this is the work done by two charges against external field. That is A7 by how this come? How this expression came? VR1. V is equal to, we have seen yesterday class, that what is the relation between electric field and potential? E is equal to minus delta V upon delta L. Okay, so rearranging it, delta V is equal to minus E into delta L. So by integrating, we will result in potential is equal to A by R. Okay, so A by R. VR1 is A by R. What is the distance of Q1 charge from origin is 0.09 centimeter na? So 0.09 meter. So what is the distance of this Q2 charge from origin was also 9 centimeter, 0.09 and A. And this Q2 charge is minus 2 microcoulomb, Q1 charge is 7 microcoulomb. So this is the work done against the electric field, external electric field. Now, net electrostatic energy is this. This is the work done by two charges against the external electric field. This is the work done against the electric field produced by this Q1 charge. This is the electric field produced by Q1 charge, and we have done the work against this electric field of Q1 charge. So this is the work done against the electric field of the Q1 charge. So this is the total work done to make a configuration. So what this will result in, after solving, this becomes 70, this becomes 20, and we have calculated in the first part was minus 0.7 joule, and the final answer is 49.3 joule. So our last topic is to find the potential energy of a dipole in an external field. So we have seen the dipole in the external field and we have calculated the torque on the dipole. Now we will calculate the potential energy of a dipole in the external field. So this is the diagram you are familiar with. This is minus Q charge, plus Q charge. This is the dipole moment. Direction of dipole moment is from minus to positive charge. This is the uniform electric field in this direction. Okay, the perpendicular distance of this minus Q charge from this center is minus A cos theta, means A cos theta magnitude, and from this positive charge to the center of the dipole distance is A cos theta. So perpendicular distance between this, perpendicular distance means this distance along the electric field. This distance of minus Q charge and plus Q charge, perpendicular distance between minus Q charge and plus Q charge is 2A cos theta. Okay. Potential energy of a dipole in a uniform external field. A dipole with charges plus Q and minus Q is placed in a uniform external field E. Dipole experiences no net force. Okay, we have also seen in the torque. When we calculate torque, we know that force on this charge is in this direction, because electric field, force is in the direction of electric field on positive charge, and force on the negative charge is in the direction opposite to the electric field. So net force on these charges are equal and opposite, so net force becomes 0. But the line of action of these forces are different. So there is torque. Dipole experience no net force. It experiences a torque that is equal to, we calculated, P cross E. P is dipole moment, E is electric field, which results in PE sin theta. That tends to rotate it unless P is parallel or anti-parallel to E. Okay, when the external torque is applied to exactly neutralize this torque. Now, torque the torque which is being applied on this dipole by this electric field. Now we are applying the external torque in the opposite direction to exactly neutralize this torque, the torque produced by this electric field in the dipole. We are now producing external torque to exactly neutralize the torque produced by the electric field and rotate the dipole from theta naught to theta 1 at infinitesimal speed without acceleration. This is somewhat familiar with the potential energy of a point charge. What we are doing in that derivation, we were bringing a positive charge from R1 to R2 at very slow speed without acceleration. It is similar. There was point charge and force, work done by the force. Now here work done by the torque. Now we are considering rotating the dipole from theta naught to theta 1 without acceleration at very slow speed, so that there will not be any rotational kinetic energy. We only want total work done is equal to the change in potential energy only. We don't want rotational kinetic energy here. So we will move this dipole with very slow speed without acceleration from angle theta naught to theta 1. Now this is the expression. Work done is equal to external torque into d theta from theta naught to theta 1. What was torque external? Pe sin theta, d theta, theta naught to theta 1. Torque external is exactly equal to the torque produced by the field, that is Pe sin theta. So Pe, after putting the limits, theta cos theta naught minus cos theta 1. Now this work is stored as a potential energy, taking theta naught as pi by 2 as reference. Now in expression we are taking any reference. We have to take the reference. So in that expression of a point charge, when we are moving point charge from infinity to any point, we are considering potential energy to be 0 at infinity. Now we have to set the reference for this one also. So we are setting the reference at theta naught equal to pi by 2. So this is the reference when this plus q charge is at that point and this minus q charge is at that point, means along this line, perpendicular line. This is the reference. The potential energy at angle theta will be, now this is, put theta naught equal to pi by 2 and theta 1 equal to theta. So this will become 0 because pi by 2 is 0. So it will result in Pe minus Pe cos theta, which is equal to minus Pe cos theta is P dot E, dot product of P dipole moment and electric field. So this is the potential energy of a dipole in an external field, that is minus P dot E or minus Pe cos theta. This can also be derived using the potential energy expressions. So we can also derive it in another way. This is the way. We have to bring the charges of both the dipoles in different way. Firstly we will bring the positive charge, then we will bring the negative charge of the dipole in the external field. Firstly we will bring the positive q charge, and this is the work done to overcome the external field of plus q charge. The negative charge, this is the negative charge we are bringing in the external field, and this is q into minus Vr2 is the external work done against external field, and this is the q square by 4 pi epsilon naught 2a that we are done. We are have done this topic, the electrostatic potential of two charge system in an external field. This is the expression for that. Now since the potential difference Vr1 minus Vr2 is equal to E into 2a cos theta, what is this? This is potential difference equal to E into dl. This is the relation between electric field and potential, which is equal to delta V is equal to minus E into delta L. So what is the perpendicular distance between both charges is 2a cos theta. I mentioned earlier. This is E. So put this value in this. This will become minus P cos theta minus Q square upon 4 pi epsilon naught into 2a. So minus P dot E minus Q square upon 4 pi epsilon naught into 2a. So second term being constant can be dropped. So this term is constant. This will not vary for any configuration of the two charges. So this can be dropped, reducing to this. So choice of theta equal to pi by 2 is natural as the work done against the field E is bringing plus q and minus q cancel out at this angle. When we are bringing this positive charge and negative charge at an angle pi by 2, then these charges, like work done to bring the positive charge and work done to bring the negative charge at this perpendicular to electric field cancel out. Okay, thank you.